All right, today we're cracking open a cold case right from the heart of physics. For literally centuries, we thought we had the laws of motion all figured out. But then, as we started pushing things to their absolute speed limits, our most fundamental law just seemed to break. So we're launching an investigation to figure out why. And along the way, we're going to uncover a hidden truth about Isaac Newton himself that pretty much changes everything. Let's dive in.
Now, for this deep dive, our guide is the incredible research laid out in the very first chapter of the book, Newton and Relativity by Sester, Clemente, and Karoff. We're going to be using their insights as our roadmap to navigate this whole fascinating puzzle. You know, every good detective story starts with a crime scene, and for us, that crime scene is the universe at extreme speeds. It's a place where the reliable, comfortable rules of classical physics suddenly and just spectacularly fall apart. So here's the heart of the mystery. Back in the late 19th century, experiments showed something really weird. The speed of light is the same for everyone, no matter how fast you're moving. Think about it like this. If you're on a super fast train and you throw a baseball, the speed of the ball adds to the speed of the train, right? But if you shine a flashlight from that same train, the speed of the light beam doesn't add to the train's speed. Its speed is absolute. This one single bizarre fact just shatters the old-school view of a rigid, absolute space and a universal ticking clock for everyone. It forces us into a whole new, relativistic way of thinking.
Okay, so with our whole understanding of space and time collapsing, our investigation turns to the prime suspect. Yep, the most famous equation in all of physics, Newton's second law of motion.
We all learned this in school, right? Force equals mass times acceleration. It's simple, it's elegant, it's powerful. But here's the thing. That equation contains a fatal assumption, one that's hiding in plain sight. It assumes that an object's mass, its inertia, its resistance to being pushed, is a fixed constant value. That implies if you just keep pushing something with a constant force, you can make it go faster and faster and faster forever. But does reality actually work that way? The answer is a big, fat no. Not even close. Inside particle accelerators, we can push particles with these immense, constant forces. But as they get closer and closer to the speed of light, something really strange happens. Just look at the blue line. Their acceleration drops off, heading towards zero. Why? Because as that red line shows, their inertia, their mass, starts shooting up exponentially. The object literally gets heavier and harder to push the faster it goes. This isn't a theory. This is hard experimental evidence that flat out contradicts the simple F equals m.
So, what does this mean? If our experiments prove the formulas wrong at high speeds, does that mean the fundamental law itself is broken? Did Newton, the Isaac Newton, one of the greatest scientific minds ever, simply get it wrong?
Well, not so fast. To find the real truth, we have to go back to the original source. It's time to do a little forensic analysis on Newton's own masterpiece, the Principia Mathematica.
And right here, this is the smoking gun. When you look at Newton's original Latin text, you find what seems like a simple translation choice, but one with huge consequences. He wrote that force is proportional to mutationem modus, which means change in momentum. He did not write mutationem velocitatis, which means change in velocity. So what's the big deal? Well, momentum is mass times velocity. It's a tiny difference in words, but a universe of difference in meaning. And this is the key takeaway, the thing you have to remember. Isaac Newton never actually wrote F equals ma. His actual law was about momentum, which is a much richer, more complete idea than just acceleration. With this new insight, it turns out we haven't broken the law of mechanics at all. We've actually restored it to its full universal glory. Let's take a look at the true equation. This is it, the real deal. Force equals the change in momentum, that's p, over time. And since momentum is mass times velocity, the formula becomes the change in the product of mv over time. What this means is you have to account for changes in both velocity and mass. You see, F equals m is just a shortcut. It's what you get if you make the convenient, but wrong, assumption that mass never changes. Newton's actual law was already built for a universe where mass could change. It was way ahead of its time.
This table sums it all up perfectly. On the left, you've got the local simplification, F equals ma. Its big assumption is that mass is constant, so it only really works in our everyday, slow-moving world. But on the right, you have the universal reality, F equals dp over dt. It allows for mass to change with velocity, which makes it valid at all speeds. It perfectly explains what we see in those particle accelerators. So let's see how this true universal law gives us a much better picture of energy. We start with Newton's real law. Then we think about the work done, the energy transferred by a force over a tiny little distance. Physicists call that ds. We combine those two ideas, do a little clever substitution for velocity, and boom, we land on this incredibly powerful new equation for how energy gets transferred.
And here is the absolutely stunning result. This single equation is basically the foundation for all of relativistic mechanics. It shows us that when you add energy to an object, that energy splits up and does two jobs at once. The first part, kinetic acceleration, is the energy that makes the object speed up. The second part, inertial expansion, is the energy that actually increases the object's mass. This explains everything.
So you're probably asking, okay, but why don't I notice this when I'm just walking around? Well, it's because at the slow speeds we live our lives at, the change in mass, that little dm term, is basically zero. It's so tiny you could never measure it. So the inertial expansion part of the equation just vanishes, and the big, universal law elegantly simplifies right back to the classic version we're all used to. The old law isn't wrong. It's just a special case of a much grander, more amazing reality.
So we've restored Newton's law, we've derived this fundamental energy equation that works everywhere. Case closed, right? We figured it out. Well, not quite. Solving this mystery has only revealed an even deeper puzzle. Here's the new problem. Our beautiful new energy equation has three things that are changing all at once: the change in distance, the change in velocity, and the change in mass. And mathematically, you just can't solve a single equation when you have three unknowns. It's impossible. It's like I asked you to solve for x in the equation x plus y equals 10. You can't. You need more information. We're in the same boat here, just with three variables. We found this fundamental truth, but we're stuck. We can't actually use it without another piece of the puzzle. So what is that missing piece? What's the key that will finally unlock this whole thing? Well, it's a law that connects two of our variables, a law that defines the exact relationship between an object's mass and its energy. And that key is the most famous equation of them all, Einstein's E equals mc squared. It provides the exact link between energy and mass that we need to finally unlock the system and solve the equation. And that raises a pretty provocative thought, doesn't it? Maybe to truly understand Newton, we first needed Einstein.